Good morning, everyone. Hello, hello. Welcome to the Wednesday of the WeAreDevelopers Congress. It's nice to see you all here for the first talk of the day at MicroStage 1. So first of all, I'd like to thank all of the partners of the WeAreDevelopers Congress for making this happen. As you all know, you can get caffeinated and hydrated at stations around the Congress, so please grab a coffee. Yeah, so today we're going to start about, I guess I should introduce myself. My name is Taylor Coley. I'm from Canada, but I'm currently based in Berlin. And I will be at the stage all day, so be sure to come check us out for the different speeches today. So we will start with a short video about the code of conduct. Okay, so this is just a short reminder to be kind and respectful to each other and to yourself today. And I would also like to remind everyone to use the Hubilo app. There's a web browser app as well as an application. And this is how we will be doing the Q&A session today. So be sure to submit all of your questions there. I'll be checking them out on my app and presenting them to Michele after his speak. So to introduce the speaker a little bit today, Michele Riva is from Milan, Italy. He's a senior architect at Nearform and a Google GDE and Microsoft MVP. In 2022, Michele published his first book, Real World Next.js, which starts with the basics and shows you how to use the multi-purpose Next.js framework to create an impressive user experience. So today, Michele is here to talk about writing a full-text search engine in TypeScript and show how to build a RESTful full-text search engine from scratch. So please welcome Michele to the stage.
Hello, everyone. Welcome to my talk, Building a Full-Text Search Engine in TypeScript. So I wanted this talk to be live coding, but I had some limitations, so I couldn't do that live, so I want to big disclaimer about that. I'm really sorry. Before we start, I already had a slide on myself, so let me introduce myself again. I'm Michele. I'm from Italy, senior software architect at Nearform, Google developer expert, and Microsoft MVP. A couple of words about Nearform. We're a professional services company based in Ireland, but we are all full remote. And we maintain a large portion of the Node.js runtime itself and many NPM packages. So if you're looking for a full remote job all over the world and want to be committed to open source, let's reach out after the talk. But before we start understanding how to build a full-text search engine from scratch in TypeScript, let's ask ourselves why. Why do we want to build something that already exists and it's well established? We already have such beautiful solutions out there, such as Elasticsearch, Solr, Algolia, and many others. So why do we want to build something from scratch and reinvent the wheel again? Well, there is a great quote from a very good scientist, Richard Feynman, which states, "What I cannot create, I do not understand." And that's the case for me. So I really wanted to understand how search engines works, how full-text algorithms works. So that's why I wanted to build something from scratch. And before I go any further, let's do a little exercise. How many of you are human beings? Great, no robots. How many of you are robots? Oh, one, spotted one. Couple of computers, great. How many of you would feel comfortable in taking an interview about data structures and algorithm right now? One, good. Two, good. 2.5. OK, good. OK, so this talk is for you, because this talk is going to be a journey through algorithm and data structures. From now on, DSA, data structures and algorithm. I know you're now maybe thinking it's a trap. I wanted to join this workshop because I wanted to see some live coding. I wanted to see how to build stuff. And now I'm trapped in data structures and algorithms. I know how you're feeling, but don't worry. This is not going to be the typical situation where you have to learn something and then throw it away right after you learned it. This is going to be actual useful information, I hope. So this is my main goal for today, to try to explain something. And also, I have another goal. Being a JavaScript developer myself, I am more and more convinced that there is no slow programming languages, but just bad DSA design, so data structures and algorithms again. So this is my second goal for today. I want to convince you of that. So what is full-text search? So Sybase.com states that full-text search is a more advanced way of searching a database. Full-text search quickly finds all instances of a term, a word, in a table without having to scan rows and without having to know which column a term is stored in. Full-text search works by using text indexes. A text index stores positional information for all terms found in a column you create the text index on. If you feel a bit confused about what we just said, don't worry, because by the end of the talk, you will be able to understand properly everything we just saw. Again, hopefully. So before we start, let's see a couple of choices. So if you have to implement full-text search in your application, please use one of those. There is Elasticsearch and Solr. Both are wrappers around Apache Lucene, which is the text engine itself. Elasticsearch and Solr provides code distribution, RESTful APIs, and whatever, and they are all open source, except for Algolia, which is a closed source product, but it's brilliant. So if you're looking for a full-text search engine, this is where you want to look at. So these are the well-established and popular full-text search engines out there today, but there is also a new generation of full-text search engines from where I took some inspiration for this talk. For example, Sonic and Meilisearch. They are both written in Rust. They are beautiful solutions. So if you feel brave enough and want to try something new, this is where you want to go. There is also kind of interest in the JavaScript community for building full-text search engines. So we also have some good products in JavaScript. Lunar, Minisearch, Fuse, you can use them in React Native. You can use them on browsers, on servers, wherever you want. And these are brilliant. So I really encourage you looking into those. OK, now it's time for us to start. But where should we start? So I would say we should start by understanding what kind of data we want to store and retrieve. So let's begin with the simplest data possible. Let's start with these documents. So from now on, objects will be called documents. I have some movie quotes from Frankenstein, Dirty Harry, Forrest Gump, for example. And from now on, we will concentrate on the quote part. So let's say we will be building an index to index, of course, the quote from the document. So the first thing we want to do is to tokenize our input, right? So when we tokenize an input, we split the sentence into multiple tokens. So individual words, as for now, we will call it token. As you can see, we do remove all the characters, and we will only leave numbers and words, and letters, sorry. So no exclamation points, no single quotes, nothing else. Of course, you could keep everything else, but it makes things a bit harder, and we want to start slow, so that's a good place to start. After we do that, we can lowercase all the tokens. Of course, that won't allow us to perform case-sensitive search, which sometimes is not an issue. We can avoid this step if we want, of course. Again, for the sake of simplicity, just lowercase everything. Then we do remove all the duplicates. There's no reason to keep it's alive twice. We store the reference of it's alive, and we can say, OK, it appears twice. So we can also store a number saying that individual token that we removed appears like once, twice, 3 times in the sentence. So we can have more, if I search for it's alive, this can be a better result. After we remove duplicates, we can start with other optional steps that I want to illustrate. For example, we could remove stop words. What's a stop word? So stop words are a set of commonly used words in a language. Example of stop words in English are a, the, is, are, etc. Stop words are commonly used in text mining and natural language processing to eliminate words that are commonly used that they carry very little useful information. So let's see the slide again. As you can see, for example, from the first quote, we remove its, because there's no useful information in its, but there's a lot of useful information in alive, so we'll keep that. We'll also remove got, to, do, I from the second quote, and was, a, of, what, gonna from the last quote. Of course, it's optional, again, but we will do that. After we tokenize, we proceed with stemming. So stemming is the procedure of reducing individual tokens to their stem. So for example, if we have lucky, we stem it to luck, because we want to store, we want to avoid duplicates. So if I store lucky and luck, they have the same meaning, basically. So we want to store them once. For example, in the last quote, we had mama. We convert it to mom. And we cannot decide to keep both, of course. But if I'm looking for all the movie quotes containing the word mom, spelled correctly, I want to find this one. So I will stem it so that mama becomes mom. And I can search for mom and still have a quote from Forrest Gump. Chocolates, plural, becomes singular. So chocolate. Of course, that depends on the language. And of course, you might have a good knowledge on the language you are going to insert into the search engine. And for example, is there anyone speaking Finnish here? One, good. I have a slide for you. But for example, I don't speak German. I don't speak Finnish. So it might be difficult for me to stem those words because I don't know them. So let me introduce you Snowball. Snowball, it's a beautiful open source library written in C that performs stemming for us. An example in English, so it's easy for everyone here. So consign, as you can see, becomes consign. Consigned in the past becomes consign again, because we only want the stem of that word. Consigning becomes consign again, and so on. How many Germans are there? Good, I have a slide for you too. So I will keep that for a couple of seconds if you want to look at it, so you can better understand how stemming works in your own native language. How many Italians? Wow, OK. I have a slide for both of us. So this is how stemming works in Italian, for example. And as a promise to my Finnish friend, this is how you perform stemming in a language that I personally don't know. I'd love to, but I don't know it. So I use Snowball. But of course, sometimes you don't know which is the language you are going to insert the text in your index. So you might want to use something like Node Language Detect, which allows you to automatically detect the language to perform the stemming in. So after we tokenize and stem and remove stop words and duplicates and lowercase, we end up with that result. So from it's alive, we now have alive. And I can't remember the original quotes, so I won't repeat them. But as you can see, we have very few tokens here. And at this point, we say, how do we want to store this data, right? We want fast retrieval when we perform searches, fast insertions. And this is where data structures becomes important. So from now on, when I talk about data structures and algorithms, they will be represented by monsters, because we are all scared of those topics, right? But don't worry, because they're going to be super easy. So let's make a quick example. Let's say we have 6 documents. We know for sure that in one of those documents, we have a property that includes the word chocolate, and we want to find it. We could do that in a linear way. For example, go into document number 1, index 0, and say, is there the word chocolate in that document? Nope. Let's go number 1. Is there? No, it's not there. Number 2, neither. 3, 4. Oh, it's in number 5. So time complexity, in that case, it's O(n). That means that if we have 1 billion documents, the worst case scenario for us is to scan 1 billion documents. And as you can imagine, this is not fast. So this is where I want to introduce hash maps. Hash maps are like Swiss Army knife of data structures, often overused, a lot of good memes. So that's a good reason to understand how they work. So hash maps are commonly used to store data in key-value pairs. So let's get out of the search engine context for a moment, and let's see, for example, my favorite things. Animal, my favorite animal is dog. I have a dog, it's called Linux. It's beautiful. I miss him so much. And it's another joke. That's true. So my favorite animal, dog. My favorite book, Algorithms to Live By. Color, language, city, and food. So we can say we will create an array of a fixed length, for example, let's say 6. And we want an hashing algorithm to hash our key in a way that it will return a number, where the number is greater than or equal to 0, and it's less than or equal to the array length. Why do we want that? So let's say we hash the word food. It will result with the number 5. So we will store food in index number 5, so 6th position into array starting from 0. So we hash the key and store the value. We do the same for language. Gives us 3, so index number 3. Book gives us 4, index number 4, then color, then animal, and city. Of course, it might happen at a certain point that 2 keys results in the same number. This is called a collision. And we can work around to that in many different ways. There are techniques where you typically create a new hash map inside the hash map, where you just store informations into an array and then loop over them. But it's not the best solution, in my personal opinion. But let's keep things easy. Let's say we had 6 elements, and we stored them without any collision. Now you might be thinking, the hashing algorithm must be really, really hard, right? But actually, it's not. 11 lines of code, it's all you need to perform. I mean, it's not super performant, but explains well how it works. So you basically create a number out of a string, where the number can't be greater than the maximum length of the array. So for example, if you perform the hashing of food with a size of 10 for our array, it will give us 2. Book will give us 7. Hello, Berlin gives us 9. So one important thing to notice is that when asking for a key, we know the exact position of its value inside of the array. So it's not only convenient for storing data, but also for retrieving data in O1, so in constant time. So the time complexity, it's constant. So for example, I might say, OK, where is city inside of my array? And the hashing algorithm will say index number 2. So as you can see, we exactly know where the value for city is. And we can do the same for food, chocolate. So we can find chocolate eventually in O1, which is not actually true, because that's not enough for finding chocolate inside of an array of documents in O1. So that's why I want to introduce another data structure. We need to introduce inverted index. So let's say we have a regular hash map where the key is the ID of a document, and the value, it's an array containing all the tokens in a document. If we want to find chocolate in those documents, we have to go into document number 1, look if there's chocolate. No, there's just alive, so not the case. Then number 2, then number 3, and eventually we will find it in number 3. But as you can see, this is linear. Again, we want constant access, time complexity for assessing those properties. So we basically swap the key and the values inside of an hash map and create an inverted index, which works the other way around. So we store the tokens as keys and say, OK, in which document can I find the word alive? Document number 1. In which document can I find the word you? Documents 2 and 3. In which document can I find chocolate? Document 3. OK. So as you can see, in just one move, we can retrieve the document containing this data. Again, there's another problem. We are not optimizing for space. So what I mean by that? Let's take an example of this input. We have intersect, interstellar, intergalactic, international, intervene, internal. We might have interview, and whatever. As you can see, we are repeating many letters, right? There is a common prefix amongst all the tokens we are inserting. How do we? That means that if we insert in memory this data, we will have multiple duplicates for basically no reason. So we are wasting a lot of space, and things get slower. So trees to the rescue. trees are not important only because they're beautiful data structures, but are also another good source of memes. So I do encourage you looking into trees for that mainly, but also for optimizing for space. And so in that case, I want to introduce the prefix tree. So let's take the following example. We have the following tokens: private, primark, prime, primate. And as you can see, they all share the same common prefix, which is PRI. So every single letter in our word can be considered as a node in our tree. So that means that we have our root node, which is the orange one. I hope the colors can show up correctly. Not the best choice for colors, I know, sorry. So the root node, and after the root node, we have the letter P. The letter P is linked to the letter R, which is linked to the letter I, then M, and then E. And as you can see, E is green. It's a green node because when it's green, it says that's the end of a word. When we want to insert in our tree, for example, primark, so we have prime, we want to insert primark, we don't need to duplicate the prefix. We basically have the common prefix until PRIM, and then create two children at M level. We create two branches. One goes on the right, E, so this is the end of one word, and then primark, so ARK, on the other side. If we want to insert, for example, primate, we branch at the A level. Let me show it again. A now it becomes primate. Then we want to insert private. We create a new branch under I. If we want to insert something that doesn't share a prefix with those words, for example, art, we can just do it at the root level. So we create another branch under the root node, and we insert art. And if we want to insert artist, for example, which not only shares a common prefix with art, but the entire word, we can just do it. Looks like a linked list right now, but actually we have T, which is a green node that says, OK, this is an end of a word, but also I have a child, so there is an entire other word after me. And we can use prefix trees as an inverted index to store a reference of a token in the document. Let me show you how. If we have primark, for example, which appears in documents 1 and 3, or primate, which appears in document 2 and 4, at the end of every individual word inside the node, which imagine a node like a JavaScript object, we can store a documents property containing a set of documents where the entire word is contained. So it's pretty easy, right? Now, I talked about TypeScript at the beginning. Talk is cheap, show me the code. Oh, OK, Linus, let's do that. So let's create an interface for our node. Let's start with that. We basically create a tree node. Prefix tree are also known as tree, T-R-I-E. So from now on, I will call them tree. So we basically have a key where the key is the single letter representing the node. We have a reference to the parent, reference to the children nodes, documents, which is a set of documents, and if this is the end of a word or not. We then have a couple of methods for getting the word and removing documents inside the node. We also want to create an interface for the tree data structure itself, which uses tree node, for example, as a root node, and then methods, basically. Insert, contains, find, remove doc by word, remove. I will show you later where you can find the complete implementation, of course. So if we want to implement the interface, we can basically do that. So we create children using map. Please, when working with JavaScript, use maps, because every single time you go change the shape of an object, that causes overhead. So you don't want that, because it's going to be really, really slow. And maps are basically hash maps, so are faster. And also documents. We say we want to store the reference of all the documents inside, referencing this node. So we can use set, because we don't have duplicates. There's no reason to keep duplicates. And also, set has faster access to individual elements in the set. So let's start with the constructor. We basically assign the key to the node, and then the get word algorithm. Let me show you how that works with a GIF that I tried to create myself, so it's not beautiful. Sorry, designers. So we basically start from the end node, and we traverse the tree, meaning we read the tree from a child to its parent until we find the root node. So let me show you the algorithm for a couple of more seconds. So we basically read the word from the end till the start. So remove doc, it's really easy. We just enter the documents and remove one document. I won't go on with this one because I don't have time. At this point, we need to implement the tree data structure itself. And I wanted to do that explaining recursion. But sadly, recursion, it's not implemented in any major JavaScript runtime, except for one. So the TC39, which is the technical committee responsible for evolving the JavaScript language, has standardized tail call elimination, which is a technique in which you can perform recursive calls at the end of your functions and optimize it for recursion. But again, no one ever implemented it except for Safari. So good job, Apple. Now let's fix other bugs. But if you want to, I know you know what I'm talking about. Great. If you want to build a full-text search engine which only works on Safari, you can use TC. Otherwise, I really discourage you doing that. So let's start creating a tree. Start with a root node, which has no key, so empty string is fine. We then create the insert algorithm. So basically, let me explain in a very shallow way. But again, I will share the code with you after the talk. We basically insert a new node, and if a node already has a child, we look inside the child map, and if there is a child containing the key we want to insert, we go on that branch. Otherwise, we create a new branch. If we want to find, we basically start from the root node, and let me show you the slide first. So basically, we go inside A, for example. Let's see if there's another child. Yeah, let's go there until we find the full prefix. When we find the full prefix, we go through all the children and then use the getWord method to read the tree from the last word to the first one, just like we saw in the previous slides. So now we have a tokenizer, a prefix tree, but we don't have typo tolerance, which is important because as a non-native English speaker, I often misunderstand things. For example, if you talk me about, I don't know, race or raise, there is a slight difference for me as an Italian. So sometimes I can just misspell stuff when I write, or I can just have a mistake in writing. For example, instead of writing word, I write WRLD. But still, I want my search engine to be smart enough to understand how to retrieve the correct documents. This is going to be scary, right? We have to introduce dynamic programming. So what is dynamic programming? Educative.io states that dynamic programming is an algorithmic technique for solving an optimization problem by breaking it down into simpler subproblems and utilizing the fact that the optimal solution to the overall problem depends upon the optimal solution to its subproblems, which looks so messy, right? And we are not even close to what is coming next. The Levenshtein distance, as known as edit distance. Wow, Kermit is going crazy at this time, you know. So the Levenshtein distance, as known as edit distance, is an algorithm that calculates the last number of edits operations that are necessary to modify one string to obtain another string. Let me give you an example that I took from a YouTube video, which is brilliant. Again, I will put the reference in the next slides. If we have moon, and from the word moon, we want to create the word lions, how many operations, how many edits I have to make to that word? The answer is 3. Let's see why. And by operations, I mean insertion, deletion, and replacement. So we start with the letter M. We replace M with L. So we have loon. We then replace the first O with an I. So we have lion. And then we insert S at the end of the word. So we got lions, 3 operations. we just use our intuition. How do we compute that? How does a computer know that these are the steps we need to take to transform moon into lions? Let's use the dynamic programming table, where each cell is a sub-problem. So as you can see, we have 2 capital lambdas. It means empty string, basically. And every sub-problem can be described as following. So D, which stands for distance, of 2 and 2, means from MO to L, how many operations I need to make. 2, I have to change M into L, and then add O. So the edit distance between MO and L is 2. OK, let's try to answer now. How many edits do I have to take to make to create O from MOO? Anyone want to guess? Yeah, that's correct. 2 operations. So we remove remove M, remove the first O, and keep the last one. So basically 2 operations. So from an empty string to an empty string, how many operations? 0. From an empty string to L, how many operations? 1. We insert 1 element. From an empty string to Li, 2 insertions. So the edit distance is 2. Then 3, 4, 5. We got lions, where to get from empty string to lions, we have 5 as an edit distance, because we have 5 insertions. Now let's go the other way around. From M to an empty string, it's 1 deletion. From MO to an empty string, it's 2 deletions. So edit distance is 2, then 3, then 4. How do we do that? This is where things are getting interesting, right? So the edit distance of D21 can be calculated using this formula. I don't have a computer science degree, so I have no idea what's written in there. I had to go through many blog posts to understand that. But basically, it says that the minimum edit distance is defined as the minimum of 3 operations: deletion, insertion, and replacement. So minimum of 3 operations. Let's keep that in mind. So to get there, we can either delete L, we could either insert a new letter, or we could change replace. So insertion, when doing insertion, it has a cost of 1, plus the cost of the letter we already have. So 1. We have 2 in total. So the cost for inserting is 2. The cost for deletion, it's the same. So deletion by itself costs 1, and the other value we have, so deletion is 2 in cost. Replacement, which costs 1 as an operation, as an edit distance operation, costs 1 plus the distance between 2 characters. If the characters M1 and L, which is again 1, are the same, so M and L, as you can see, they are both 1, the cost is 0. So 1 plus 0 is 1. We can go on like that. The difference between I, which is 2, and M, which is 1, is 1. So the replacement, which costs 1, plus the difference between M and I, which is again 1, it's 2. So the edit distance in that case is 2. And we can proceed again and again until we are in that situation where we have O on one side and O in another side. And at this point, we have to use that little part of the formula, which basically says, OK, let me tell you that very shallowly. You can bring the value from D42, which is equal to D31. So you could bring the value from the upper left corner, and it will just work fine. Until you repeat this operation until the end, you will end up with that value in the bottom right corner, which is the total edit distance for the word. So we can clearly see which operations we need to take to the optimal solution at this point. We replace M with L, so 2 and 1, as you can see. We replace O with I. The second O and N can remain, so no operations here. We then insert DS, and that is how you compute the edit distance using dynamic programming. You can do that with every possible word in the dictionary. So horse and poser, for example, at the distance of 3, race and race, again, at the distance of 2. And now you might be thinking, OK, not super easy, but the algorithm itself must be hell, right? It's actually pretty easy. 33 lines of code, quite well optimized, not the best one you'll see today, but quite well optimized, and you can do that with no problems at all. So one nice thing about the Levinstein algorithm is that we can perform these operations both on strings and trees. So if we decide to keep an inverted index as a source for our data, we can basically, when a user inputs something and it's misspelled, for example, we could take a dictionary and look at the similar word in the dictionary. Not the best solution. Or we could take all the tokens we already have in our database and compare every single word to the misspelled word we just inserted using the Levinstein algorithm on strings. Or we can do that using trees. There is a beautiful YouTube video, which I highly recommend to understand better these concepts, which I know it's a bit abstract. So I do really encourage you looking at that, because it's really beautiful. There is also the official paper that lets you understand more mathematically speaking how that works. And it's called Simple Fast Algorithm for Edit Distance Between Trees and Related Problems. It's from Zhang and Sasha, two beautiful engineers. So at this point, we were talking about full-text search engines in TypeScript, right? So what is the product after we build all of that? Well, the product is called Lyra. Lyra is just another full-text search engine written in TypeScript by me personally while at Nearform, and it's now in beta. It's the first time I present this publicly. So you can already install it from npm at nearform/Lyra. And you can just insert stuff easily. Supports promises. It's very, very fast. We'll see some benchmarks later. You can perform insertions and searches, deletions, replacements, whatever you want. And it's really, really fast. Let me show you a benchmark I did yesterday. So I took the International Movie Database, 1 million titles of movies and TV series, and tried to iterate 1,100 times. Well, sorry, 100,000 times, searching believe, for example, in the titles, and it can retrieve like 1.8K's result in 41 microseconds. Not milliseconds, microseconds. It's not because I'm good, because I'm a horrible engineer, but because data structures cannot lie. And if you want your code to be very performant in JavaScript, in Python, in Ruby, in Java, in C++, in Rust, in whatever, you just have to learn the right data structure and the right algorithm. So I do encourage you to test the beta phase of Lyra by installing it on npm. As always, I'm looking for contributors. So if you want to contribute, it is fully open source. And I'll leave the slide for 1 quick second so you can take note if you want. And now that you all have the smartphone out, I want to show the next slide for thanking you for being there. This is my book. In case you're interested about Next.js, you can reach out after the talk. And I also leave my contacts. I live on Twitter, so if you want to follow on Twitter, I'd be glad to answer any question and reach out and hang out digitally. So thank you so much.
All right, thank you, Mihaela, for that. That was great. And everyone still has the opportunity to submit a question if you have one. We have one question lined up so far. So why not use SHA-256 as a hash function and write something ourselves? OK, because you want to learn how to do that. That's why. As I stated at the beginning, what I cannot create, I do not understand. That's Richard Feynman, it's not me. But you can't think of learning something without actually gets your hand dirty. So I do encourage every one of you reinventing the wheel every single time, not for production usage, but for deeply understanding how stuff works. It is good to reinvent stuff sometimes. Yes, we are here to learn today, and I hope everyone took something useful out of this. All right, we have one question. So maybe I will listen and repeat it loudly for everyone. OK, so how can you differentiate between a stop word and an acronym?
That's a good one. Yeah, so you basically want to have a list of stop words that you want to remove. And if the acronym is not inside the stop words list, you just keep it. Or you can keep both. I mean, you can have exceptions. So you can decide to keep one and delete another, depending on the context. You can do that with natural language processing and n-grams algorithms, generally speaking. There is a beautiful library on NPM, which is called Natural. And this is a library I highly suggest you looking at because it helps you doing that specifically. It's also very well written. So if you want to take a look at the source code, you will deeply understand how it works. So I'm sorry. Maybe it's not the best possible answer, but this is how I do it.
OK, I have one more question online.
OK.
So is this viable in memory-constrained environments? For example, huge documents in Electron limited to 4 GB?
Well, if I understood correctly the question, this is 100% in memory. When you start writing to the disk, it becomes really messy. You have to think about code distribution, sharding, and replication, and consistency between nodes. So it's really, really difficult. And I don't think, as for now, that I will support this write to disk. It will have a plugin system, though. If there's anyone crazy enough to want to try this, I do encourage you submitting a PR for a plugin for that.
All right, I think those are all the questions that have come in. Thank you very much for your time today. And let's give them a final round of applause.
Thank you.